Okay, our last topic is rational functions. And without a doubt, this is the most difficult topic for people in this unit. So make sure you go back and replay this video, if need be, several times to make sure you have this stuff down. Also understand that you are going to be expected to graph functions like you see below here without a calculator. Alright, so these are examples of what we call rational functions. So this is when we have a polynomial divided by a polynomial. Okay. These types of functions have asymptotes. They have asymptotes embedded in their graphs. Now, an asymptote is a boundary line that the function approaches at the extreme ends but never touches. Okay? We're going to use dotted lines to represent our asymptotes, and there's two kinds that we're going to look at: vertical and horizontal asymptotes. Okay? So, for the sake of introducing this topic, we're going to use a calculator to help us graph these. We're also going to look at the table of values for some of these. If you have a calculator, great. Make sure you follow along and use it. If you do not have a calculator, you want to make sure that when you get back to school, you input these functions into y equals and you investigate the stuff like I'm taking you through right now. So, our first task here is we're looking to find the location of the VAs, which is an abbreviation for vertical asymptotes, and we're going to express our answers as equations. We're also going to look at horizontal asymptotes on this page, which you'll actually see is on the next page of your notes, but we're going to combine everything onto this one page. The functions don't change. Okay? So our first function here, I want you to enter this into your calculator into y equals. Make sure you put parentheses around your denominator. So if we were to look at a table of values for this function to help us plot some points. In particular, I want you to look around -4, -3, -2. -4, if you were to plug that in for x, you get -5 for y. -3, it's going to tell you that there is an error. In other words, it's undefined. If you were to plug in -3 into this function, you get 5 divided by 0, which we cannot do. And then we have another point here, -2,5. So that's what the table is showing us. Okay? Dot, 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 etc. So if we were to focus in on what's happening here at -3, if you were to now graph this, you have what's called a vertical asymptote at -3. Now the calculator is not going to draw that dotted line, which we call a boundary line. It's not going to put that on there for you, but it's there. Okay? It's a line that our function is approaching at these extreme ends, but never hitting. So way up here it's getting very close to it, and way down here it's getting very close to it, but it's never going to hit it. So we say that we have a VA at x equals -3. Alright, that is the equation. X equals -3. Recall from your algebra days that, please excuse my dog barking upstairs, recall that if you have a vertical line, the equation for it is x equals whatever that number is. So that's where we have a vertical asymptote. Now there appears to be another boundary line, and that other boundary line happens to be on the x-axis. This is known as a horizontal asymptote, and the x-axis, my dog is so annoying, sorry. The x-axis is the line y equals 0. So the idea here is we're looking at the other extreme ends. Okay, we're looking at right here and right there. Okay, so the idea behind a horizontal asymptote is if we were to try to figure out what's happening to y as x gets really big. So as x approaches infinity, what is happening to y? So arrow to the right means we're approaching it. So as x approaches infinity, so what I would like you to do is go to your table of values and go to your table setup and put in 100 for x. If you were to put in 100 for x, the y value would be 0.04854. Okay, so it looks like it's getting pretty darn close to 0. Try putting in 1,000 for x. Again, go to your table set and start it at 1,000. Well, this is going to give you a number even closer to 0. So 0.00499. So the idea there is as x gets really, really big, y appears to be approaching 0. Same thing on the other end here. If you were to plug in something like negative 1,000, if you were to plug that into your calculator in the table of values, you'd get negative 0.005. So that's another value very, very close to 0. So we say that we have a horizontal asymptote at y equals 0. So that means as x gets really, really big, our function is leveling off. It's approaching the line y equals 0. Okay? So this particular function has a VA at x equals -3 and an HA at y equals 0. Okay, so let's take a look at our second one here. We're not going to worry about the table of values, we're just going to graph it. So if you were to input this into your calculator, don't forget your parentheses around your numerator and your denominator. If you were to graph this, you would see that at +2, we have a boundary line. We have a VA at x equals +2. And you would see that at y equals 2, we have what appears to be a horizontal asymptote. So we have an HA at y equals 2. And our function would look something like this. Okay. Keep in mind, notice how each asymptote gets used twice. So the horizontal one gets used on this end and on this end. The vertical one gets used up here and down there. So each asymptote gets used 2 times. Alright, so just up here, each one gets used 2 times, okay, in a graph. So that's our function, and you could easily find your intercepts to help you make a more accurate graph. We talked about how to do that. So here we have HA at y equals 2, and we have a VA at x equals 2. So I want you to begin thinking about how we can determine where a VA is without actually looking at the graph. And then the same thing for the HA. Let's go down here. Take a look at C. So once again, use your calculator, put this into y equals and graph it. This graph actually is going to have 2 vertical asymptotes, one at x equals -2 and one at +2. So we have a VA at x equals -2 and we have a VA at x equals +2. And you would also see that there is an HA, horizontal boundary line, at y equals 0. Okay, so the graph itself, if we were to sketch this, there's a y-intercept in there, and we have 3 separate parts to it. Okay, notice how each asymptote is being used 2 times again. Okay. So the last one, we're actually going to, I want to have you change this. We're going to turn this into y equals 3 plus 1 over x minus 5. Okay. So if we graph this function, again, using your calculator, you have 3 plus 1 over that quantity, x minus 5. You would see that your VA is over here at 5. So VA, vertical asymptote, at x equals +5. And at positive 3 for y, we would have an HA. So HA at y equals positive 3. Our function, again, you could find your intercepts very easily, and in doing so, they'll help guide your graph. Okay. Here's the other portion. Okay. So this is just a sketch, okay? It's not perfect, but just to give you a feel for what this would look like. And don't forget, your graph has to be a function, meaning it has to pass the vertical line test, okay? So you want to make sure that it's always passing that vertical line test. Alright, so now we go back and we need to come up with first a way to find vertical asymptotes without using our calculator. So if we look at our first example, the VA was at x equals negative 3. The second one was at x equals 2. The third one, we had two of them. We had 2 and negative 2. And the last one here was at 5. So can you think of an algebraic way of getting the vertical asymptotes without actually plugging it into your calculator? Hopefully, you're thinking, well, I'm just going to set the denominator equal to 0. Alright, that's all you're going to do. You're going to set the denominator equal to 0, and you're going to solve for x. Okay? Notice that right here with the last example. This plus 3 that we see, this is just going to take our graph of 1 over x minus 5, and it's going to shift it up 3. So you have a vertical shift up 3. So if you were to take this 1 over x minus 5 graph and only focus on this, alright, that plus 3 just shifts it up. So you have a VA at x equals 5 there. That plus 3 shifting it up is not going to affect the location of your VA. Notice in the previous example that x squared minus 4 in our denominator, if we were to set that equal to 0 and solve, you'd get plus and minus 2. And the two previous ones, same idea. If you were to take your denominators, set them both equal to 0, you're going to have the location of the VA. Now, horizontal asymptote rules are a little bit more difficult. So, let's go back to our first example. Stupid dog. So, with our first example here, keep in mind that the idea behind a horizontal asymptote is we're trying to figure out what is happening to y as x gets really big. So I'm going to have you jot this down up top here. So with an HA, what we're trying to figure out is as x gets really big, what's happening to y? Question mark. Okay? So that's the idea behind horizontal asymptotes. As x gets really, really big or really, really small, what's happening to y? So think about in our example, part A, if I were to put in 1,000,000 for x, if I put 1,000,000 in for x right there, adding 3 onto it's not going to have much of an effect. I'm going to have 5 divided by something very, very big. Well, 5 divided by something incredibly big, alright, so 5 divided by something very, very big, call it infinity, is basically going to give us 0. So that's why we say there's an HA at y equals 0. The bottom is very heavy, in other words. There's more weight in the bottom. So if you divide by something with a very big bottom, it's going to get very close to 0. Think of it as you have a pizza that you want to divide up amongst 5 billion people. Well, if you're lucky, you're going to get a crumb. So you're basically getting 0. Okay? So I want you to look at example C. This is another situation where it's bottom heavy. If I were to plug in 1,000,000 for x, that plus 3, that minus 4, it's not going to have much of an effect on things. The fact that if we look at x squared versus x, this is going to be bottom heavy. So I want you to write bottom heavy. If it's bottom heavy, that means you're going to have an HA at y equals 0. Same thing with up here in example A. It's bottom heavy, so HA at y equals 0. So if you put 1,000,000 in for x, there's going to be more weight in the bottom because you have to square it. So you'll be dividing by a much larger number, so your y will be approaching 0 as x gets really big. Now with let's actually jump over to D here. Same thing. If we were to just focus on this 1 over x minus 5, write yourself a little note. This is also bottom heavy. Because if I were to put 1,000,000 into that, who cares if I subtract 5? That's not going to really do anything. It's going to basically be 0. So why don't we have our HA at y equals 0 here? Well, this plus 3, we said, is going to shift it up 3. So really, the HA was at y equals 0, but then it got shifted up 3, so now our HA is at y equals 3. B is the last one to take a look at. Notice here, this is not considered to be bottom heavy. You can ignore this plus 3, ignore that minus 2. Just focus in on the 2x and the x. If I were to substitute in something like 5,000,000 for x, I'd have 2 times 5,000,000 divided by 5,000,000. Well, those 5,000,000s would divide each other out, leaving you with what we call the ratio of the coefficients, meaning the numbers in front. So if you have 2x over x, these x's divide each other out, leaving you with just 2, and it's technically over 1. So when we say the ratio of the coefficients, we're talking about the values in front of x, right, the coefficients, put into a ratio. So it's just whatever numbers you see in front. So in this case it would be 2 over 1, or just 2. That's why we had y equals 2. So we'll summarize this on the next page. So we already found all of these HAs. So let's just write here, see other page, smiley face, don't forget the smiley face. Down here, we're generalizing our HAs. So if we have a function that's bottom heavy, so you put something like 1,000,000 in for x and there's more weight in the bottom, okay, the HA is at y equals 0 every single time. Be on the lookout if there's a number that we're adding onto it, which will shift it up or down. So that's the first scenario. The next scenario, if we have what we call equal powers. Alright, this was a situation where we saw 2x over x. Those x's each had a power of 1. So if it's equal powers, the HA is going to be at y equals the ratio of the coefficients. Okay? And by the way, I think I forgot to mention, HAs are horizontal lines, so the equation is always y equals. I know I mentioned that VAs is always x equals because that's a vertical line. Okay? Now, we didn't see an example like this, but if it were top heavy, then there's no HA. And by top heavy, I mean something like perhaps y equals x squared minus 4 all over maybe x plus 3. You can see that there's more weight up top here than there is in the bottom. So this actually, if you were to graph it, would not have a horizontal boundary line. Okay? So listen to this video again if you need to. We will practice in class. Goodbye.